Hi, I'm John Moore with JHM Technologies. Today we're here to talk about another myth that's very, very popular in our industry, and it's myth number 2. Of course, remember myth number 1 being that the closure of the mold will push the fiber into place, and we've talked about that. That's impossible. You must fit the fiber tight into all the details of the part geometry, forcing the glass into the inner radiuses, and this is so important so as we can control the flow path of the resin. But, you know, the myth number 2 then is, well, we've hooked vacuum to the cavity and that's going to suck the air out. No, that isn't what happens at all. We have to understand what vacuum really is. It's a measurement, or it's an indicator there's a differential in pressure. You have the outside atmosphere that we all live in, and we're under pressure here. Now that pressure varies at our elevation. So let's just keep this consistent and simple in our thoughts. Let's talk about at sea level. So at sea level, we're all under about 14.7 psi of atmospheric pressure. So if we contain a box, and inside the box it has the same pressure as the outside of the box, well then there's 14.7 pounds all around. However, if we hook a pump to that box, to the interior of that box, and we take that pump, and it's a pump that can pull atmosphere or can pump out air, as it were. It's going to pump the air out of that box. Now we say we have a vacuum in that box. So what we have in effect done is pumped out some of the atmosphere. Now what's outside the box is trying to get inside and equalize the pressures. So we've created a differential. The differential of the outside pressure in comparison to the pressure inside. Now we use the illustration of a box, but really what we're talking about is a mold. So when we're thinking about our molding operations, when we hook a vacuum line to the mold, we're in effect pumping the atmosphere out to a given value. Normally in the Light RTM process, we pump out about half of the atmosphere. Well then obviously we've left half of the atmosphere inside the mold. That means we still have to influence half the amount of atmosphere that was in that mold to start with. We've got to instruct it, push it, do whatever we need to do to communicate to it to leave at the exit vent. Well, now how does that happen? Well, again, the myth in the industry is, well, I've hooked vacuum to it, so it's like a Hoover vacuum cleaner. It's sucking the air bubbles out. That's not how it works at all. So what we're going to do is we're going to talk about just how it works to have the atmosphere leave the mold. Now, first thing that's critical, and it's what we teach in the class, is how to create an accurate tool. I took apart here, this is a tub for a medical cell-saving device. In fact, one of our other videos online shows the Aviator, our semi-automatic machine, making it so simple and easy to inject this part. And you can watch that video in another time. But when we were done making the part, we took it off. And just moments ago here, I just highlighted this section of it just to show you how consistent the laminate thickness is. Now, we teach you how to make tools that accurate. You'll find many times in the industry tool variances in cavity thickness are the norm, and they shouldn't be, because part of the critical features needed in the process, be it conventional RTM, which we're going to talk about, or RTM Light, which we're also going to talk about, which is a more recent innovation in the industry, it's still based on having tools that were built accurately. So that's critical. So just what we consider accurate. Well, there is always some tolerance involved. Now this mold was sheet waxed to 120 thousandths. So I'm measuring right there at 117. I'm getting 124. Right there, I'm at 124 again. I'm at 130 right there. 127. So you see, we're within 10, 12 thousandths of target, which for this particular application was plenty accurate enough. With a bit more precision on our process controls of vacuum and pressure, again this was injected, you'll see in that video, under the first time injection. It's mentioned that is the first part that came off that mold. We could get that down a couple 3 thousandths variance. The point is the tool was built accurately. Key number 1. Key number 2 is to understand then what influences the air to leave. Well, let's talk about our 2 different types of processes for a minute. When we look at a mold here, let's just talk about a flat shape. It doesn't make any difference if we could add geometry. We'll get into that in a moment. But let's say RTM, what everyone considered the original process, resin transfer molding. In that case, we would normally inject in the center of the part, and then these would represent the outer perimeter. So what we would do is we would inject in the center, and we would exit at the 4 outer perimeter corners. Very typical. Someone said, John, we've got this box. Where are we going to inject? I'd say, well, we inject the very bottom. In this case, we would have injected, in this case, straight down here, and we put a vent here, here, and in the other 2 corners, the other half of the box. Would have been very standard, would have gone on about our business and never thought twice. And we did it that way for 20-some years until RTM Light came out. But think about what's going on here. We inject in the center, the resin then flows outward in typical ring fashion, filling. But the point is, it's diverging away from the injection point being here. RTM Light, what's the difference there? Basically, it's the same mold, lighter structure because it doesn't need to hold back as much pressure. We've drawn atmosphere out by pumping some atmosphere out with a vacuum pump, which we talked about. Now, in that case, we don't inject in the center. And this that I'm about to tell you is the fundamental difference between RTM, which was a diverging flow path from the point of injection diverging away. The biggest difference between the 2 processes is the RTM Light process is a converging flow path. What does that mean? It means that we inject around the perimeter of the fiber pack, around the outer edge of the mold. Where here we vented at the outer edges of the mold, RTM Light, we inject around the edges of the mold. Subtle in sense, huge in performance. Let me show you. We now inject around the perimeter, so we have the largest area, all focused heading towards the center of the mold. What this is doing then is we've got the largest area continuing from the fill towards the center, all focused on getting to that center point. I'll illustrate it this way. Take a crowd of people, walk into a room, and we're all trying to get to the very center. Well, what's going to happen? We're all crowding in. Well, the ones in the leading edge are getting elbow to elbow. They're getting tighter and tighter, looking around saying, hey, but they're fighting to get through the glass is what's happening with the resin and the mold. Ourselves, we're just trying to get through here without bunching up with crunching each other. Ones in the back are saying, come on, let's move, let's move. We're all saying, look, we're getting as fast as we can. So the ones in the back start looking around. They say, well, where else can I go? They see a little spot over there. They go over there. Well, think about the resin doing the same thing. The resin's flowing through the mold. The leading front edge is jammed up because it's trying to get through the glass. The resin in the back's trying to go. It can't go forward fast enough. So in a converging path, the front leading edge becomes a restrictor, forcing the global area of wet resin behind to look for a void. Very critical. That is what would allow, let's say for whatever reason, we had a dry spot here. Resin flowing right around.